All right, sign into the Kahoot, please. We're going to get first question pretty early on. Hello, PowerPoint. Where did you go? All right, I'm going to start talking about the final project today. I'm not releasing the code or the assignment. It's not going to be much of a final project, really. It's just sort of a slightly, maybe more interesting assignment kind of thing with a little bit longer time. So the original plan is I wanted you guys to write some machine learning code. I'll talk about what that means, and a GUI to control it. And then I started writing the code. I'd done something similar to this recently in Python, and then in Java it got a little complicated. There was some technical subtleties that are kind of interesting, actually, to be honest, but tricky. So the new plan is that I'm going to sort of discuss some of these technical subtleties and hopefully work you through my thought process of sort of why I want to do things a certain way and show you how to do it. And then today and Friday, and then release the assignment on Friday. Basically finish up a little bit with the machine learning code and then have a more emphasis on the interface. So I'm kind of cutting down the stuff you need to implement as the time gets shorter here. Yeah.
For the A9 line assignment, did you want to submit A19 for this?
No, that was a typo, and I did finally correct that at the very end. I had one before that was called A10, and I somehow deleted one character instead of two. But if you submit it as A19, we'll deal with it because that's what it said, right? Okay, so there will be something else coming out here, but we're running a little bit behind on it. So let's do a Kahoot. I want to talk about something that came up from the Lights Out game. So I'm going to start here. There's only 8 people signed in. It's not very many. All right. So I haven't started the question yet. In your light button, it needed to communicate with the Lights Out game, and there was probably some sort of method to say what was going on inside the light button, like whether it was on or off. And there's different ways you can do this. I have some choices on the right. Maybe one of those matches up with what you did. And I'm curious if you think one way is better than the other. So let me start this one. All right, so think about how you would like to talk to a light button to figure out what its state is.
So assuming that we used exactly one of those, we probably should pick that one?
If you use exactly one of those, then yeah, I hope you're confident enough in your choices to stick with that one. Talk it over with a neighbor here in the 30 seconds you have remaining. Okay, so a lot of you picked the third choice. Let's talk about each of them real briefly here. So you have to think about how you want to use this thing. Typically, it's going to be some sort of if statement, right? So maybe there's a b.getColor, and you can say if that was equal to, white or something like that. And that works. Right? I could have, if I want to figure out, if in the Lights Out game I want to know if a button was on or off, I could say, if the button I'm looking at, get color equals, actually probably do dot equals here, right? Equals white, then do something to it. What do you think about that choice? So those of you that liked it, maybe say why. For those who don't like it, say why. Someone tell me something here. Let me hear from somebody else. That's okay, sorry. All right, so you voted. I want you to, you just push buttons here.
It just seems kind of unnecessary. Like you could do it a lot easier.
So maybe it's overkill.
It's a bit extra.
We don't care what the color is. We want to know whether it's,
it's like,
is it on?
Not, yeah.
Is it not on? Kind of thing. So this works, but I'd claim that this is more information than we really need. Yeah.
I feel like that's kind of restrictive as well. As you have to have a white color because you do something different to the design.
So later changing stuff, if you wanted to go orange and green, then all of a sudden you're changing all those colors, kind of thing. Okay, so another choice was on or off. So someone like that. About 20% of you like that. So someone tell me why you liked it. So that I can mercilessly destroy you. All right. Someone who didn't like it, what's wrong? What do you not like about that?
Well, on or off, true or false doesn't necessarily represent on or off. So if the variable's titled on or off, but you get true, well, which does that mean?
Yeah, what does it mean? That's the real question, right? What does on or off mean? Well, yes, it is on or off, right? It has two possible cases. It's either on or it's off. So this would always be true. If that was expressed as a Boolean expression, it would always be true, right? It is on or it is off. So I'd have to go look at the documentation to figure out what returning true means in this context. And so when I read it out loud, if the button is on or off, make it off, make it on. I don't know what to do with it, right? So it was a reasonable stab in the right direction. You're getting out a true or false value, but I'd say this was poorly phrased. And you need to think carefully about how you phrase things so your code kind of flows more naturally. Is on. We love it. Right? It says, when is this going to be true? When the button is on. When is it going to be false? When the button is not on, right? So the question you're asking here is answered by the result it gives. And so you can read this. If button is on, do something for a non-button, right? So the way we made the method name there kind of tells you how to interact with it and what's expected. And in fact, some people say a lot of times if you return a Boolean value, you should make it this kind of question, is something, and then it's true or false, all right? So just keep that in mind. That's one little handy way to think about making these kind of methods. Is something. The last one returns an int. One means on equals one kind of thing, right? At least the method tells you what to expect for an on button. One means on. What's wrong with this one?
What does not one mean?
Well, yeah, there's a lot of other possibilities besides one. It could be 2 or 0 or something like that. But here I think the larger flaw is that we don't have to make up little values to mean true or false. Why don't we have to make up those values? Because we have Boolean already. We already have something that means true or false. So don't make up something else that means true or false when the system provides something for you that means true or false. So here, I'm inventing my own true or false value, 1, and I could have said 0 means off or something like that, right? And there's no need to go down that route. Just use the concise, well understood things that Java provides for us. But the larger point here is that the names you give things matter a lot in how people can use these things. So spend a little time thinking about what it should be. I go back and change the names like all the time. And sometimes I don't converge to a better answer, but at least I'm thinking about it, right? Any commentary or questions on that? All right. Let's do a little experiment. I'm going to show you a picture, and I want you to tell me the expression of the person in the picture on the Kahoot, okay? So, and you only get like, maybe it said 20 seconds on this. What is the expression here? It didn't show up yet? Let's go on. There's 96 answers. You're the only one out. 10 seconds left. Make it work. 5 seconds. All right. It was a bit of a tie between neutral and smiling. Let's try another one. If I had done these in a different order, you would have been. I know it's hard to see that too, huh? All right. Man, those of you that picked angry must really freak out when someone's really angry. Last one here. All right, some of you are hanging on to smile. No smiling that one, but a few neutral people, but mostly surprised. All right, so the reason I'm saying this is because, in general, we were pretty good at picking an expression, even though, for example, like that one's, not exactly what I'd say, a super happy face, right? But a slight smile. The majority still picked smiling. Almost everyone here picked neutral, and almost everyone here picked surprised. So, as humans, we're good at doing these sorts of tasks. I actually have one more that's not a Kahoot one, but so you all know the Zuckerberg robot meme thing here, right? I don't know what that is there. Yeah, so. Okay, so. So in general, humans are pretty good at activities that require intelligence. And in fact, that's something how we just sort of define intelligence, things that humans are good at doing. Computers are not good at doing intelligent kind of activities. Now, I want to say this is a little bit unfair because really anytime a computer gets good at something, we say, that doesn't take intelligence anymore. So there was a time where people thought, oh, be able to read handwriting, all the mysterious changes in people's handwriting was like something that humans did, but computers would be bad at. Computers had to have block letters that were very exact to understand. And now the post office scans, a billion letters a day and can read the worst scrawl better than I can. And they just say, oh, that's just optical character recognition. That's not intelligence, right? Playing chess was like, okay, we already know, I'm not very good at chess. It takes super smart, intelligent person to play chess well. And so that's obviously an intelligent thing. And then, humans start losing at chess to computers, and they're just like, the computer is just looking at a lot of possibilities. It's not intelligent anymore. And then there's stuff that really seems kind of hard, like diagnosing cancer, where as a human, we have to spend 12 years doing medical school and fellowships and stuff like that to get good at diagnosing cancer. And all of a sudden there are sort of these systems that do a pretty good job of looking at radiology pictures and diagnosing cancer. And we're like, it's just looking at a bunch of data, making it work. I will say, people worry about machines taking over jobs, and truck drivers are kind of in a panic because of self-driving cars and things, but doctors, a lot of doctor stuff should be really worried because they're the ones that cost a lot of money and computers are starting to get pretty good at it as well. And I think the most recent example is this driving a car kind of issue, where you're just thinking, embedding yourself in the world and trying to understand all the conflicting kind of information you're getting and making a plan there is really tricky and seems to be the kind of like the synthesis of information that requires intelligence. And now, cars are on the verge of being accepted, driven by computers, right? Sad case of that person that got killed in Arizona, notwithstanding. So, this has been a goal of people in computer science for a long time, make computers act more intelligent. And like I said, it's sort of a little bit of a self-defeating activity because as soon as people solve some problem, then they say, no, that you didn't solve anything there, move on to the next hard problem, right? A little comic, artificial intelligence is overrated. We find most people prefer the user-friendly advantage of artificial stupidity. And people saying, what's that? Okay. So traditional AI has its roots back in the 50s and 60s, really, and was traditionally a sort of proof-heavy, math, very formal kind of approach. They really tried to say, this is this thing, what are the relationships between these things, and define it in a kind of formal way. A problem with that is that people found this kind of strict classification was tough. So, it would say, if it flies, it's a bird, and then, therefore, it has feathers. They try to make that kind of formal reasoning about things it was observing. Of course, the real world is very messy. There's flying fish, there's bats that don't have feathers, airplanes are not animals at all, ostriches have feathers and are a bird but don't fly, and that kind of stuff just makes all this sort of very formal AI kind of fall apart. And these systems sort of had very limited domains where they were useful. So a more modern approach is called machine learning. It's not completely distinct from AI. They coexist in some reasonable way. But machine learning's goal really is to take lots of data, and by lots, it's like Facebook kind of data, 90 million users kind of data, a billion examples of something, and they run statistics on it. So there's all these sort of pretty clever statistical techniques. They're not formal math proofs, but they're just like trying to winnow out sort of patterns and things like that. So they look for patterns, they do some sort of classification, and they learn based on all these sorts of examples. And by classification, it means like you can say, is this a stock that I should pick, like sell or buy or hold, And this machine runs and it runs tons of data and it says, it gives you a classification. This stock is something you should buy. And then it goes buys a million of these things and the market crashes and all that kind of stuff. So but that's the goal of machine learning. Not formally proving something's correct, but more just like counting on a lot of empirical evidence to show that it might be useful. So let's look at a quick example of classification. And again, classification is given some things. You want to decide, are these fruits? Is it an apple or an orange or a tomato? Is it something that's healthy or diseased? Is it a stock you want to buy, hold, or sell? And there are a lot of different approaches. Some just work on the data by itself without any sort of supervision. Some they work on some sort of training set where some expert has sort of classified these things, and then it learns from sort of the human's classification. So as a sample problem, let's say we have some fish at a packing plant. A boat comes in, dumps a big load of fish on a conveyor belt, and we want to sort them into two different kinds of fish, right? So we want an automated system to do this as opposed to some human having to stand there and toss fish 12 hours a day in sort of dangerous conditions. So one possible procedure is we want to somehow learn what's important or how an expert might classify these things. And so if you're looking at these fish, how might you as a human decide that they're different? Like, look at those pictures. What's different about them?
Their color's different and their outline.
So the color's different, and color seems like something that a computer could kind of measure, right? You could take a camera and kind of look at it. The length is possible, although you might have baby fish and big fish, but those actually are the two measures that this example decided to use. I would have picked something about those fins or something like that, the 2 fins or 1 fin, but maybe those are too hard to measure on a conveyor belt with a camera and they don't want to do that kind of thing. So if we take a fish and we can measure its sort of lightness and its length, we get some numbers based on that, right? So there's going to be some number associated with that. And that means we can plot it. Well, let me show you. So here's the goal. Fish come in, camera looks at it, some robot arm picks them up and very neatly places them on a conveyor belt. And they move down and get turned into cans of fish. So if we have those two numbers per fish, we can have a number for the lightness and a number for the length. And we can take a specific fish and decide where it falls on this graph, right? That's what this means here. So one plot here means that is a fish with a lightness of 1.2 and a length of 2.7 or something like that, right? Now, an expert may go and take a collection of fish and classify them as to what they are, whether they're salmon or sea bass. And so we start up with this training set of data that says, here's all the salmon that we know, and here's all the sea bass that we know. And the question now is, given an unknown fish that we measure its lightness and length, how can we decide whether it's a salmon or sea bass without the human anymore, just by doing some math kind of things, right? So if we add in a new unknown fish, and we're going to do that with a triangle here, how would you decide, based on what's known and what's unknown, how might you decide kind of like what kind of fish this is? Any ideas?
So you can draw a line between the two data sets, and you can see if it falls in one or the other.
So okay, so there's something what we call clustering, right? So there's sort of this line, well, that sort of separates the two data sets. And in fact, if that were a straight line that separates them, we call that linear data. And this is nonlinear data because the line that separates them is this big, curly thing that goes like this. So the line is sort of generally helpful, but it's not perfect. Like in this area, it's sort of mixed up a little bit, right? But there's a line that splits them, and so you can say which side of the line you fall on. So that's a reasonable idea. But sometimes those lines are hard to make, right? I don't know how to make that line by using math, so I need some maybe easier idea. So what is this thing like?
It's like a salmon.
Looks like a salmon. Well, you're cheating here.
Well, no, I guess I'm using a line method in my mind.
So why do you say it looks like a salmon?
If I just kind of split.
Because you joined the line again. So without this line, I don't know how to make that line. That's the hard part. That line is hard. It's a big curvy line. It's sort of tricky. So what else can I do here to figure out what I am?
Just look at the closest data point to it.
All right, so one way is saying like, what am I like? And right now, I am like, the closest thing to me is a salmon. And so I'm going to say, well, if I'm like a salmon, then maybe I'm a salmon. So that's sort of a pretty reasonable approach. And actually, what this does is actually sort of locally approximates that curvy line just in the neighborhood, basically. It lets me say, which side of the line I'm in right at this point, kind of thing. Now, this isn't a perfect solution. So here I have another, well, actually it's the same fish, but I pretended it has different attributes, right? And so here's the unknown one. Its closest one here happens to be the sea bass. And so I'm going to say it's a sea bass. And all of a sudden you buy your can of fish and it's salmon instead of sea bass, and you write to the company and you're angry and stuff like that. So this is not a perfect solution. There's places where the data can kind of lead us astray. So we can do a little bit better job by maybe looking at a couple of the closest neighbors, right? So we're assuming there's possibilities where there's sort of these outliers, these weird cases, but if there's enough data and you look at enough of the data, then maybe that sort of overcomes statistically sort of the problem associated with looking at one item. So here, there's 3 closest neighbors, and here are 2 of them, here's one of them. Based on that, there's no clear answer. So how should I say what this fish is classified as, given that result, where I'm saying that one of them says it's a sea bass and 2 of them says it's a salmon? What can I do? It's like it's just say, don't know, kind of thing, or
Like a weighted average, the distance from each, and
so find some average of the distance to each, and
whatever has the higher value of salmon or sea bass wins.
so some sort of weighting of these things.
You could just say it matches with
salmon the majority of the time, so it's a salmon.
Yeah, this is actually how I'm saying here, vote. Vote on it. So these three get to vote, and two say salmon, and one says sea bass, and so we say it's a salmon. Now there are other tweaks to this where you kind of weight the votes according to their distances and all sorts of sort of clever things. But fundamentally, we're saying find the closest neighbors, see what classifications they think they are, and then say which one is the majority vote here. Okay? So you get the basic idea here. This is actually called the k-nearest neighbor classifier, and it's the one we're going to be using to classify not fish but other things. Let's talk about this in a little more detail. So first of all, this whole concept of sort of plotting these points, I think I need to make sure you're comfortable with. So if we have items we want to classify, those are no longer fish, in case you don't notice. That's an apple and an orange. So this is some sort of classifying fruit. Somehow we need to take the items and turn them into something we can work on, right? The computer can work on. So what do I need to do to turn this physical object, or picture this physical object, into something that the classifier can work on?
You can put its color to a value.
All right, so maybe we want to measure the color. And again, you know, is that a lightness, darkness, single number, or red, green, blue, or who knows what? But there's some number we can associate with color, and so we can get an axis on the graph. What else can we measure on one of these things here?
Texture.
Texture, yeah. So if I had, it's probably actually sort of a fancy sensor, you know, rubbing on my fruit as they go down the conveyor line. It's either very smooth or kind of bumpy, right? What else can I measure?
Max.
So it's how heavy it is, right? So I just weigh it, and I don't know the answer to that, whether apples and oranges tend to have different weights, but if they do, that's a useful kind of measure. So there's all sorts of things we can measure, and we have to decide like how many of these attributes we want to pick. So we could just pick weight, and then each object turns into a single number, right? That's the key here. And we plot them on a number line for weight. So it'd be like 0 pounds, 10 pounds at the end. That'd be a very big orange for sure. We get a bunch of these things and we measure how heavy they are. And we can plot them. And maybe the oranges cluster on one side and the apples on the other. In which case that weight might be enough to help us classify whether an unknown fruit is an apple or an orange. I think that's kind of unlikely. When I go to the grocery store, the oranges seem kind of similar to the apples. And so there's probably a little overlap there, and then we'd be in some trouble. If you pick two attributes, like weight and width, then they appear as points on this 2D graph, right? So we're representing these objects in different spaces to show what we know about them. So in this case, that apple has a certain weight and a certain width, that orange has a certain weight and a certain width, and we take that whole big complicated thing and basically just reduce it down to some number and say this is what we think of as an orange and this is what we think of as an apple.
Wouldn't color be the most optimal classification?
Yeah, but maybe, I don't know, a lot of industrial cameras are just black and white, so maybe there's some trickiness there, right? I'm not saying this is the optimal classification. But if we have two of them, then we're in this two-dimensional graph space, and we can reason about them looking for clusters and such in this two-dimensional space. Now, we talked about a lot more kinds of attributes. For example, we have 15 attributes. Weight and width and softness and sugar content and acidity, the juice and smoothness and color and smell. You know, all these things we can measure, right? We can associate some number. Ooh, fruits. Different fruits then appear as points in a 15-dimensional space. All right, so we had our one-dimensional space with one attribute, a two-dimensional space with two attributes. And then if we have all these attributes, that's a point that lives in this hyperdimensional space. Now you shouldn't be scared about that space. It's not one that we can draw a good picture of, right? We can draw our 1D line, we can draw a 2D plot, we can kind of fake a 3D point. And then we sort of run out of ideas after that, like 4D, 5D, we don't know really how to draw it, but those points live in that space and you can look at clusters in that 15-dimensional space. It's actually a great place to work in. A lot of my PhD work is actually working in these sort of like 12-dimensional spaces, and it's a great place to live. You know, so it's just the number of attributes you're kind of measuring to think of it as a point. All right, so questions on that? Like, you kind of get the idea. Anything we can reduce it to a number, right? And then once it's a number, we can start to work with it on the computer. So, questions? All right, so, and in fact, it's fairly common to have more than two-dimensional points. Facebook has you as a number. Facebook probably has you a number with like a couple hundred attributes. You live in a couple hundred dimensional space in Facebook land, depending on what ads you've clicked on and what kind of posts you have and who your friends are and all that kind of stuff. So, you may just be a point, but you're a very high dimensional point, so you should feel proud of that. So, at some point, we need to compare these objects in some way. And one way to think about that is, we talk about like doing dot equals on objects, and there we're comparing all the fields and make sure the fields are the same. But another thing you can look at is sort of like how far apart they are. And in a 1D space, that's just sort of how far they are on the number line. In a 2D space, we can just use, basically the Pythagorean theorem, right? So here's the difference in one axis, and here's the difference in another axis. That makes a triangle. And you take the sum of the squares and then square root it, you get the distance between those points. And so distance is a very useful measure because it works in higher dimensions as well. And it just tells you sort of how close two objects are. And that's what we want to know for this classification kind of thing. Okay? Now let's look at our Canaan. Okay, so generically, if we're trying to classify something, we're going to call that a sample of some kind. So we have a sample of like a sample of a fruit, a sample of a facial expression. And a sample really has just the numbers that describe it, so where it plots on this kind of graph, and some kind of classification that it knows about. So it knows that it's an orange, or it knows it's an apple, or really sometimes it's unknown and we have to assign a classification to it to figure out what it is using our algorithm. So let's go over sort of this classifier that we did with the fish a little more formally. So we're going to start with a set of known samples, which means they have measured attributes, and they have some sort of known classification like they're an apple or an orange. We get an unknown sample. I mean, you actually have it, so it's not like totally unknown, right? And then you measure those attributes. And of course, if you gave me an apple or an orange, I don't have to measure it all and say this is to realize it's an orange. I just look at it, but we're pretending we're the computer here, right? So the computer measures its attributes. Then the computer finds the distance between the unknown sample and all the other samples. So in this case, think about going from the unknown, measuring the distance to everything here, right? We're going to find the distance to everything. And then we sort the samples by distance. So it goes from shortest distance to biggest distance. We choose the nearest, and that's something you say how many you want to look at, like 5 nearest or 10 nearest or 2 nearest. And it depends on the data and sort of how many examples you have. And then you have those k nearest vote on a classification. And that's what happened here. We measured the distance to all of them. We sorted it and found these 3 were closest. And then we had them vote on whether it was a sea bass or a salmon. Okay? Let's see. Let's do an example of this in real life. Let's classify samples as student or professor. All right? And I'm going to pick 2 attributes to choose this. I'm going to pick age and height. All right, so 0 to 75, and let's see, what you do in inches, I guess, or something. I have to think about what that means. Let's do like 50 inches to 80 inches. How tall am I? I don't even know. Let's see. 16, okay. So I'm going to plot myself somewhere P for professor here. Okay. Now I need some volunteers. Quick, I need a couple of you up here. Quick, come up. I need a couple of you. Come. Plot yourself. Put an S down for student. Okay. 72 is 6 feet. So you're an S. Quick. It's gotta be quick. Oh, a secret professor has. Oh, my example still works. You're that old? All right, so the type clustering going on here. You're going to be our unknown sample. Okay, so we have our training data classified as student or professor. And now we have an unknown person. We want to decide if he's a professor or a student. So put it just a dot or an X like somewhere, okay? Okay. So to classify the unknown, we measure the distance to all these mysterious scribbles. And I'm going to do well, I can only really pick out a K of 2 nearest neighbor. So we sort all of them, and we pick out the 2 closest, which are these 2 here. And they vote, they say, this is a student. All right, so it's a very simple process. You know, look, it worked perfectly in this case. And we should publish some papers about how age and height are a great way to distinguish professors from students. It only works by chance, kind of there, right? All right, so this isn't so bad. The math is easy. You find this distance, you sort stuff. We know how to sort stuff, and then you just pick some small ones and make that happen. Now, let's think about how to make this work from a Java kind of point of view. So we want this classifier, this KNN classifier, the code to work for a bunch of different things to classify, like fruit, or facial expressions, or stack picks, or disease diagnosis. We don't want to write a custom code each time, right? And we want to somehow store what we need to know about these kind of things as well. So just kind of roughly, how can we express some of this in Java? Like, what's fundamentally do we need to do here? Any ideas? Yeah.
Well, each thing that we're measuring, we can set it up as an integer array, where each element in that array is a different value for the different characteristics.
So each thing
Is an integer array.
has an array, I'll just say a list for now, of attributes. Is that what you're kind of saying? So a thing we're measuring, like a fruit or a face expression, has a list of attributes. It needs to know something else as well. Go ahead.
A Boolean to check what attributes are there to whatever we're looking for.
So I'd say if it has them, we're going to use them, right? We're going to claim that if you bother to enter these numbers, we're going to pretend they're useful in some ways. So maybe we'll avoid that step. We need to keep track of its classification. So you know, we have to know that this list of attributes means apple, this list of attributes means orange, kind of thing. And so when someone enters these things, we need to track that. So here we're storing a couple things. What does this imply about how should we organize this? What kind of thing should that live in? We already have a list of things and a classification. But let's say I need this for my apple I measured, and I need it for my second apple I measured, and I need it for my orange I measured. Where's that all going to live? An object, which means I need to write a class. Okay, so this is some kind of class here, right? I mean, I'm talking real basic here, like how do we organize this stuff? And then at some point when I have a bunch of things, they're going to be a list of like this kind of thing, right? So we keep track of attributes, keep track of classification. This KNN code, what kind of thing is that you need to keep track of? First of all, where is that going to live? It's going to live in some kind of class. Everything in Java, of course, is a class, so it's hard to avoid that, right? So, yeah.
That would be the graph, it tracks the two different values, right?
So this thing has to know something about that. I mean, it doesn't physically have to like draw a graph, right? But it does have to know about what? So it has to know the known samples. And that's some sort of list or array or kind of thing. And then it has code to work on that. That's all it really has to know about, okay? All right, so,
I have a question.
yeah.
When we do the K&N sorting, when we add a sample, or like when we test something, do we add that new value to our sample set? Or do we just,
I'd say if it's unknown, you don't add it to known samples.
Okay.
You keep track of it as a separate sample somewhere, right? So, we have some of these kind of things, but so classes for things to classify. What is a thing? We need to kind of think about that a little bit more. Can it be an integer? Not really, because an integer doesn't have a classification, it doesn't have multiple attributes. So we need some kind of custom class to hold this data, and K&N code needs to know about how to talk to that class through some kind of standard interface, some standard way of saying, give me a sample, give me classification, give me something like that, okay? So let's kind of think about this now actually in code for a couple minutes. So I'm going to make, instead of a K&N classifier, which has some complications, let's start with an easy classifier. And the easy classifier just knows about one sample. And it's a known sample. And then we're going to ask to classify that known sample. And so it gets the classification from the sample and says what it is. All right, so this is not much of, this is not really anything. But it's a structure that's sort of analogous to the K&N classifier. So this one has no subtleties at all. It says, give me a piece of fruit that knows it's an apple. And then when you ask for what it is, it says, I'm an apple. All right? Do you guys get it? It's a real basic classifier, like even more than this. So let's kind of just try that out. So let's see. What does it know about? It knows about fruit. So I'm going to have to make a piece of, I need to define what fruit is. So fruit holds a classification. We're not even using those measured attributes, so I don't even have to store those things, right? This is such a simple classifier, it doesn't use any information to do the classification. It just says what it is. So I'm going to initialize the piece of fruit with its classification, and then we have a getter for that classification. All right? So this is, again, a super stripped down version of what we need for the K&N classifier, but it has the same interaction between the code that classifies and the things that we're classifying here. So for example, in here, I can make a piece of fruit. Apple equals a new fruit, and I pass in the classification for it, and then I make the easy classifier what do I call this? Easy equals a new easy classifier of this apple. That's the apple object, not the string apple, right? And then I can ask easy to classify that thing. Go, do it. Pick, okay. Of easy.get classification. All right. It's okay if you're confused why I want to do this because it's so dumb, right? But you should at least understand that I'm trying to have a classifier that holds something and knows how to classify it, and I'm going to test it, and when I run it, it says it's an apple. Okay, so that's good. Now the problem is, I want this easy classifier to also work for a face class, and a stock class, and a student professor class, all those things. What can I do to make that happen? So I want it to work for a face class, which means I could write face there, but then it doesn't work for the fruit class, right? What can I do?
Templates and
then the easy interfaces?
So let's make it a generic, right? So instead of making this just fruit or making it face, we're going to say this is a generic class that takes different kinds of things, and it's going to hold one of those things, and we need to initialize it with one of those things, and it returns the same. And now I make a piece of fruit, and I say I want a fruit version of the easy classifier. I'll put it there as well. And it almost works. It's complaining about something here. Under get classification it says, get classification is undefined for type T. That's because type T is a very general type. It could be a string. It could be, I can pass anything I want in here right now. I could pass in string. I could pass in integer. And none of those things have a get classification method. So somehow I need to make this work for everything that is has a get classification method inside it. Okay, do you see the problem here? I can't just sort of make it all totally generic and then expect it to have specific kind of behaviors here on the object. So that's a problem. So we want to force fruit and face and other things that we want to classify to have a method get classification. We want to guarantee that any kind of type that we're trying to use in the easy classifier has a get classification method. That way it will always work. So we can make them inherit from a superclass, an abstract class that has a get classification method, and then all our classes that we're going to use in the classifier have to inherit from that superclass, so they're forced to implement the get classification method. So let's give that a try very quickly here. So I have a public abstract class sample, and I want to just add the abstract public string get classification in here. Okay. And now in my fruit, I'm going to say it extends sample. And that means I have to override get classification for this class to be valid, right? So this sample class, again, forms some sort of contract that says anything that inherits from me must implement this. So fruit must implement this. And that means that if I only let things that inherit from sample be here, then they have to have this get classification method. Okay? Now, right now, there's nothing here that really forces that to be something that inherits from sample. It just says, give me a type T, integer, string, whatever. But there is a way in Java to do what's called a bounded type. And I can say, this extends sample. And that means that this type that gets passed into this generic has to extend the sample class. It has to inherit from the sample class. So this adds a restriction to the kinds of things that this generic can handle. Okay? And you'll see, so this, like I said, it's getting complicated, right? Now notice, it's not complaining anymore, because it knows that if T extends sample, then T must implement the get classification method, and this call will always be valid. If I try to pass in a string here, it says bound mismatch. The type bound is wrong. The type string is not a valid substitute for the bounded parameter T that extends sample of the type easy classifier. All right? So Java enforces a compile time for this restriction to work. That's an important concept with generics, this bounded type thing here. All right, so we're in better shape now. My classifier works for all things that have a get classification method. That can be fruit and face and all that stuff, as long as they inherit from sample. We're only halfway there in terms of the complexity of generics here. On Friday, we're going to get really painful. So hold on. Okay, that's it for now.